science image, reference image of the sky, and every time the science image is the image of the sky, let's say yesterday, and the difference image, which is the difference between both. Okay, using that triplet, we pass that triplet through a convolutional neural network, and the output of the convolutional neural network is concatenated with some metadata. Okay, that metadata is contained into the files that are currently processing by ALeRCE and contains different characteristics of the object, such as, for example, the star galaxy score, the magnitude from the PSF feed, galactic coordinates, etc. Okay. When all of those are concatenated, we create prediction, and this method it's currently giving predictions for 5 classes, 5 different classes, such as AGNs, supernovae, variable stars, asteroids, and bubbles. Okay. As you can see here, the overall accuracy is more or less 95% of F1 score. And as you can see, the accuracy, for example, for AGNs is 93%. For most objects is up to 93%. For the supernova objects is 88%. Yeah, please. Okay.
So you take the images, you get the difference, and then you compute a series of features that come from the convolutional neural network. Do you also use any ancillary information about the objects, sort of the things like the host galaxy and things like that? Okay. Okay. So. Okay. Do you concatenate those features to what comes out of the neural network?
Yeah, as I said, the triplet of objects is passed through a convolutional neural network, and the output of the convolutional neural network in different versions, as you can see here. For example, the original version rotated in 90 degrees, 180 degrees, etc., are all concatenated using that metadata that it is contained into the main files. Yep.
So some of those features are related to the host galaxy, not exactly the host galaxy, but for example, the first two are the score for the first, second, and third closest source in pan-stars, and the second one is the distance to those.
It's very nice. If you go to the matrix of predicted versus the truth value, yeah, I'm very surprised that you're that accurate. Can you please tell us how you even define those, things? Because it often occurs that sometimes, they're having unambiguous definition of them might be not that trivial. Yeah.
Yeah, some of the objects that we have here, ALeRCE has a very specific taxonomy that we are gonna see later. And the objects that came from that taxonomy are labeled by human inspection. So the defined taxonomy was, the taxonomy is previously defined, and then the classes are defined by the taxonomy. Yeah. I don't know if that answered the question. Okay, let me show you the taxonomy later, and maybe it will be clearer when I show it.
Sorry. I think very simply, my question is, what are the characteristics that you have that if if an unknown source fulfill all of them, you just call them AGN, Because sometimes it's really tricky,
Okay, I have not the specific astronomical details there. I'm more from the data science machine learning side perspective. Maybe Guille, you have an answer for that?
Okay, yeah. So it's I'm going to try to make it short, but it's a long answer. So there are in ALeRCE we have a lot of astronomers from different fields. So they are in charge of creating the training sets. They usually go and download a whole bunch of catalogs for each of these, and then they visually inspect it, as Manuel says. Then, when the model, before putting the model into production, what we do is we grab a whole bunch of data that's unlabeled, and then we pass that data through the models, and then we make sure that they make physical sense. Like, for example, variable stars are usually in the galactic plane and stuff like that. So we try to make it as good as we can, and usually we do it like this: like we grab unlabeled data, we throw it to the models, and then astronomers make sure that this is they basically curate or check that the model is performing as it should be doing.
Thank you. And yeah, one of those validations, for example, when we classify objects, to put it into the galactic plane in order to see if they has a physical sense. So I want to show you how easy it is to dig into the machine learning pipeline. So you go, for example, to snhunter.alerce.online. And here you can see the top 100 SNs that were early classified within the last 25 hours. So you can go here. And you can see, for example, the triplet that was used in order to classify the objects and perform validation as visual validation, for example. Okay.
And those are submitted to TSM.
Yeah, those are submitted to TSM in order to perform further follow-up. Okay, when first alert is triggered, then when more alerts came into the pipeline, a cross match is performed in order to match the object with other public catalogs. Okay. Then magnitude atmospheric corrections are made for some light curves, and feature computation is made in order to compute some characteristic of the light curves. Some of the features are, for example, statistical aggregation features and some astrophysical features that are made fitting some astrophysical parameters into the with the data. Then it's everything synchronized. And when we have an object that has more than 6 alerts, either in the red and or green band, we perform late classification. Okay. This is the main result for the late classifier. This is a random forest, a balanced random forest, and this is the taxonomy that I was talking about. The algorithms goes like this. The first thing we do is to classify between top classes, which are transient objects, stochastic, and periodic objects. Okay, each of those classes has subclasses. For example, for the transient objects, we have the supernovae type 1A, supernova type 1BC, etc. Okay. And for those objects, we first train a random forest using the top classes in order to classify between transient, stochastic, and periodic. And then for each object, we train, for objects of each of those main classes, we train a random forest classifier for the subclasses. The full probability is given by the probability of being of one of the subclasses, given that the object was previously classified on the top class. So this is those are the main results for this classifier, which works with alerts. Okay. Also, we have forced photometry classifiers. CTF is now when CTF now triggers an alert. Brings the first photometry 30 days ago. Okay, so when an alert is triggered, we have now more data than before. We have not just the alert, but rather 30 days of data. Okay, so two classifiers are used in order to classify the first photometry data through ALeRCE. Okay, the first one is the same model that, as I told before, is the random forest classifier, the hierarchical random forest classifier that first classify between the three classes: stochastic, periodic, and transient objects, and then between the rest of the subclasses. The other classifier that ALeRCE has is ATAT, which is a transformer classifier, a multimodal transformer classifier that takes two things. The first thing is the light curve, okay, the full light curve of the object, and also the computed features for that object. Okay, both inputs are passed through their respective transformer model, and then are concatenated, and different loss functions are computed for the tabular data, the features, the light curves, and both together. Okay, and the sum of the three loss functions are minimized together in order to obtain the full predictions. Okay. This is the ALeRCE's platform. I want to show you how cool and easy to access is. So let's say, for example, we are gonna use the Likert classifier, which is the classifier we have seen. And we want to get all the supernovae with a probability greater than 0.6, and let's say 8 alerts, minimum 8 alerts, and maximum 3,000 alerts. So here are the candidates. We can click on the candidate and we can see the full light curve. We can see the image, the last image we have from the object. We have the triplet here, which contains the template image, the difference image, and the science image from that date. We can search for specific dates in order to see the image of the objects and the specific date. And also we can see the probabilities for each of the classifiers that we have. Okay, so as you can see, is pretty cool. Whoa. Those are the main results for those classifiers. This is the random forest, balanced random forest classifier for first photometry data. And this is the transformer classifier for first photometry data. It's kind of difficult. We have a lot of classes here being classified in each of them, but as we can see here in this plot, it's easier to see the F1 score, and as a function of the length of the light curves, that means the F1 scores in function of the days after the trigger, after the alert is triggered. So as you can see here, for example, in the random forest classifier, when we have like 100 of days before the trigger, we get an F1 score of 0.6362. And our transformer classifier, evaluated almost at the same date, has an F1 score of almost 70% of accuracy. So the transformer classifier is the classifier that gets better results. But in order to use both classifiers, we have to take into account this, the confusion matrix. In order to, we need to look what specific object we want to get, and what classifiers it's better at classifying that specific object. Okay. So also, we have not in production yet, but we hope so. We hope to have it as soon as possible for casting services. An anomaly detection method. Okay. The anomaly detection method, what does is to take the light curve, okay, at each time step, the features that we have talked are calculated, and the features, the data is split into two sets. Okay, a training set and a test set. Okay, we have three anomaly detectors, one for each of the top classes we have seen in the taxonomy, one for the transient, stochastic, and periodic main classes. Okay, and for each of those classes, a specific anomaly detector is trained in order to see if we can find weird objects that do not belong to those classes. Okay. Our main anomaly detector methods are autoencoders and specific multi-class deep supervector data description that we have introduced. And it's this model, okay? What we do is that, for example, if we are in the transient, we are training transient anomaly detector, we will have 4 classes, supernova type 1A, 1 type BC, superluminous supernova, and etc. So what we do is to pass the data through a neural network, which was previously trained as an autoencoder, and we define centroids from the data passed through the encoder. So we pass the data, and we define that most of the data is clustered around a specific point into a hyperplane. So we define the center of that data into the hyperplane, and we minimize the distance between all the objects that belong to that class into this hyperplane. Yeah. Okay. So the objective there is to cluster the data that comes to that are from a specific class each other, and when a new point comes through the model, we compute the distance of that point into each of the hypersphere we have defined. So if the distance of the point is high, we will have a high anomaly score. Okay, if the distance is low, we will have a low anomaly score. So we can define the full distribution of the anomaly score. We can define a specific cutouts in order to separate normal data from weird data. Okay. Another service is the parameter estimation model, which are not currently available, but will be released. Okay. What is the future of ALeRCE? Well, we have released the features we have been talking here about. Now currently public available in Zenodo, so you can look for the features. For many objects, the full computed feature for many objects here, so you can get all the data for the objects here. Okay. And also, the anomaly detector will be released very soon. Okay. That's it. I want to ask your question now.
Do you have questions for Manuel from the audience or online?
There.
Hi, thank you for the talk. So the two confusion matrices for the two classifiers looked at the cursory look very similar. So can you elaborate on why having two classifiers has an advantage over having one? So thank you.
Yeah, in general, for the transformer based classifier, It works a little bit worse on and supernova or transient objects than the other classifier. I think that's like the main difference. Respect to the variable stars, periodic and stochastic objects, both classifiers are doing pretty well, as you can see here in the diagonal of the confusion matrix. But mostly here is the main difference, okay, which are mostly transient objects. For example, TDE, superluminous supernova, supernova type 1, type 2, and etc.
Yes, by the way, Guillermo here also works on ALeRCE, so
Yeah, and the other thing is that, so for example, when we had the two confusion matrices, at some point we were discussing whether we should put only one model in production or the other. And we decided to put both of them in production because the one on the right has an overall performance that's better than the one on the left. But the one on the left has a hierarchical taxonomy. So the one on the right, it just classifies everything, right? But if you want to look for only, let's say, transients, it's easier to do if you use the model on the left.
For the great talk. I'm just this curious spectator to the machine learning system, so apologies if the question is naive. You mentioned that there is you can track time rapidly time varying sources through this method.
Mhm.
So is there a limitation on like this time scale of that method? So can you track like sub-second variability, sub-minute, sub-hour?
Yeah.
So do you have a limitation on that aspect? Thank you.
Yeah, I mean, for the features that are computed through the pipeline, for some of the features, we need at least 6 detections in one of the bands, and there are green bands. So as the minimum number of detections, I think we need 6 at least to complete the full list of features that we have, okay? In terms of the maximum length, I think the limitation is given by the training set that in which we have trained the data, not by the models itself, but for the training sets. I'm not sure what was the full length of the ATAT, the last training. I think it's here. It's here. Here it is, 2,000 data points. Yeah. Yeah.
Days. Okay. So since we have force photometry data, the models used to work with at least 6 detections. So we need 6 points in the light curve. But when we started getting force photometry data, we have 30 days prior data. And that means that the shortest light curve is around 11 points. So we don't have that restriction anymore.
Axel.
Yeah, thanks a lot for the talk. I have one question related to the outlier detection or anomaly detection. You mentioned that you're looking at a distance to a certain cluster, right, in a high dimensional feature space. My question is, what about the curse of dimensionality? Right, like, I mean, in high dimensions, you would basically expect everything to be an outlier. So I was wondering whether you've looked at this and like how well does it work, or whether you've considered like reducing dimensionality, for example. And
Yeah. Well, what we did was to use an autoencoder, was pre-train an autoencoder. Okay. So the first step is specifically, is to pre-train an autoencoder in order to reduce the dimensionality. So with the autoencoder train, what we do is to pass the data through the train autoencoder, and in the latent space we compute the centroids of each specific class. For each class, we compute a centroid in that latent space. So yeah, in that reduced space, we is reduced space. We have the dimensionality of this space is less than the input space. We perform the separation between normal and abnormal objects.
Okay, thanks a lot. Yeah, that makes sense.
I do have a quick question about the general transformer concept here. I believe you've said that in your transformer approach, you would feed a transformer. You would feed two transformer, one with the light curve itself, and another one with the computed features that you do manually. We know that transformers can be pretty good at summarizing sequential data sets. And my question, well, I have two questions. The first question is, to what extent does the transformer acting only on the light curve performs well? How redundant is to also add the manually added features? Because I would expect the features that the transformers get, the embeddings from the transformer, to be a good set of features for whatever downstream task you want. And the other one is about, if you train these two transformers, how do you combine the embeddings of the two in order? You just pass a single set of embeddings as the features for the classifier? Thank you.
Yeah. Okay. The transformer is trained. The input is the full light curve plus the features. Okay. So when we have an object, we pass everything through the transformer, but we compute separately the cross entropy for the light curve, the cross entropy for the features, and the combined cross entropy. Okay, so our transformer, basically using that approach, can classify using everything separately or everything together. Okay, and we have in the main paper, which has been published today, accepted today, we have comparisons between how it performs using only light curves, only features, and everything together. Okay, and in the three cases, the best classifier was the classifier with everything together, which is okay. We perform augmentations coding the full curve in different with different in different time steps. Okay. So.
That's interesting. I'd be interested to know what is it that the manually computed features add.
Yeah.
To what is it that the transformer is not really learning from the light curves directly that you get? But yeah. But in the meantime, I don't want to drag my question too long. If anyone else has questions, points. Okay. Shall we just read the paper all together?
So on the features, you have two types of features. You have the metadata, which here stands, it's MD, and you have the features calculated by the broker, right? But you can see this. I think this line is really informative. This one over here. This is the model only using the features, the metadata, right? So that means that there's no temporal information there. And this is the first, these are the different models, okay? The ones on the top, can you go to the top? So these are the differences. The green one is it's without using features, and the blue one is using the features. Now, when we try this on CDF, the features are more informative. This paper in particular shows results on elastic, the simulations for the LSST. Okay, so that means that there's not much difference between using and not using the features, but there is a difference between using and not using the metadata, which you can see below on the plots below. It does. So on the tabular data, it goes, you can use only the metadata, only the features, or the features plus the metadata.
So maybe the answer to my question is the metadata. That's what.
Yeah, that's really important, the metadata.
Any other comments, questions? Critics about the food? No? Okay, well, if there are any more questions, thank you, Manuel, very much. Let's thank him again. And Manuel will be around this week and also next week for the AstroAI workshop. So if anyone wants to talk to him, and Guillermo is also here only today, but around in the week, not too far away, I hope. So in case someone wants to chat with you, thank you all. And thank you, Manuel. Yeah. And see you next week at the workshop.